starting the science section of our learning in physics. We could be learning about space. So what is space on a very, very basic level? It's just nothingness, a vacuum. Of course, there's a lot more to it where space isn't truly nothing, but for the sake of this video, to make it short, let's just think of it as nothing for the time being. So if space is nothingness, then matter is the opposite of space. It's something that takes up space. And within space, there are fundamental forces at work that give us the results of our reality. So we're going to go over space very briefly and give you an idea by putting kind of matter in it to kind of see how it interacts. So, in space, you're dealing with a three-dimensional world. This is just kind of a little picture I did to get an idea of space. So, you have a grid here, and it represents all three dimensions, X, Y, and Z, which is up and down, left and right, side to side, and back and forth. And those are our three dimensions, and space, although isn't endless, is vast, and it's expanding. Now, give you an idea. Let's just say that I create an object in space. Let's say I made an object in space, right? And remember, these lines, this is all just empty space, but these lines represent to give you an idea of depth, height, and length. So we have this object right here. And we'll paint this little square here green right there. So that's where it is relative to space. Say it's its origin, point of origin. And we'll just call that 0. 0 longitude, latitude, and depth. And we'll just call it length, which is this, or length is up and down. Width is left and right, and depth is back and forward. 3 dimensions. The origin point we'll just say is 0. Pretend that each square is equivalent to 1 length or width, or whichever direction it goes. Positive is up, negative is down, and vice versa. Square was our origin point. Moved 1 length toward you, so +1 length, or depth, and this would be +3 depth. From the origin point, this would be -1, -2 depth, -3 depth, and this depth could represent inches, feet, miles, whatever you want. Okay, so now I'll be dealing with depth, or height, I apologize, and depth. So as you can see, my mouse is not acting up. 1 second. That this square is the origin point. So 1, 2, 3, 4. That's 4 on the positive side of width. All right. And then we could go up 3 squares, because now we're going on height. 1, 2, 3. So it'd be this square right here, right? And I'm just trying to represent an idea of objects relative to space in 3 dimensions. And these squares, as you get smaller, these squares could be any size. It works in nanometers, it works on any size, inches, it's all the same. So the world works in 3 dimensions. I was just trying to get kind of a little bit of a visual. And here's depth. So if this was the origin point, go back here. So +3 -2 depth, and go up as many. Let's say like 4 to this square here. And so objects can move within space, and you use X, Y, and Z axes to get an idea of where things are located in the universe in this demonstration. And these lines just kind of give an idea of where things are in space, because otherwise it'd just be a black screen, because space is just a void. Now, let's say you had an object in space. Let's say this is a ball, could be anything, just for the sake of example. What would happen if it was just in the vacuum of space? Well, it's pretty simple. Absolutely nothing. It wouldn't move, it wouldn't rotate, it would just stand perfectly still in that precise location. Remember, we're talking about X, Y, and Z location, because we're working in three dimensions. It will stay exactly in place. And with that ball that's farther away, that will also stay exactly in place, because the same fundamental laws that are controlling, I guess that's, for lack of better words, the universe, apply universally. So that means whatever's laws are affecting this orb here is affecting that orb over there, and vice versa. When looking at space, though, we see that it's extremely complex, with life and stars exploding and supernovas and energy and all this stuff. There are many things happening in the universe. Like the space example I gave is very simple. Nothing happens, really. Even when putting an object in it under the conditions of space, nothing happens. Yet when we look at the universe, it's extremely complex, though starts at its simplest form. So what brought about all these complexities? Since space by itself has no real effect or cause, or at least effect anyways, there are fundamental laws of nature that create causes and effects, starting with the simplest, and we're going to be going over that. At one point, the entire universe was condensed into just one singularity, a little tiny speck, essentially. It was very, very, very dense. And I mentioned space being nothing, but it really isn't truly nothing, because you could actually measure it, like I did in the example. However, outside of the singularity was outside of the universe at the time, because it was so small. And that could not be measured. That truly was nothing. Then the universe expanded at a very high rate, and is still doing that to this day. And that is because the law of motion. That which is in motion will stay in motion. The first law of motion dictates that an object that is completely still will remain completely still. But if it's moving, it'll move in that exact same trajectory, going a straight line, going the exact same speed forever, unless an outside force acts upon it. So like unless it collides against something, say an asteroid that's going through space, going 3,000 miles an hour, it'll go that speed consistently in a straight line, but if it hits another asteroid, let's say, it'll change trajectory and speed and everything, and then it'll go that speed in that trajectory forever until it hits something else. And this is a universal law of the universe, which creates a chain of cause and effects. The second law is the acceleration is proportionate to the amount of force that's applied to it, and is inversely proportional to its mass. And mass is the measurement of the amount of matter that is in an object, and matter being anything that takes up space. So here's a diagram of an object moving through space in a straight line at a consistent speed, and it'll continue going that same trajectory at that same speed forever. Now let's say the object collides with yet another object, like here. The green object was still, and then once they hit, it changed their trajectory and their speed. The pink ball moved, transferred its energy, and they're both going in different trajectories. So Newton's second law is force equals mass times acceleration, or F equals ma. Force, represented by F, is measured in newtons, which is N. Mass is measured in kilograms, which is represented by K. And acceleration is represented by the letter A, which is in meters per second squared. Also apologize for the glare. Tried fixing it, but nothing I do would help. But anyways, so there's a nice little triangle here that kind of helps you break it down. Force, mass, and acceleration. So if you're trying to figure out the force, you'd cross this out and do mass times the acceleration, the mass being the weight and the acceleration. And if it's the other way around, if you're trying to figure out, say, the mass based on the force and acceleration, notice there's a multiplication and a divide symbol. It would be force divided by acceleration, and vice versa. If we didn't know the acceleration, it'd be force divided by the mass and you figure out what the acceleration would be. So if we have 10 kilograms moving at 4 meters per second, we know the mass and the acceleration, so we could figure out the force. So it's just mass times the acceleration. If we had an object at the mass of 10 kilograms, and it was moving 4 meters per second, it would be 10 times 4, which is 40 newtons of force in order to make a 10 kilogram object move 4 meters per second. Here's the second problem. 1,500 newtons, so we know the force. Moving at 5 meters per second, which is the acceleration. So we got to figure out what is the mass. So if you look at this triangle, little diagram here, what you do is you divide the force by the acceleration. If you do the math, 1,500 divided by 5 meters per second, or 5, you get 500 kilograms. So we found out the mass based on the force and the acceleration by dividing them. Now we're going to figure out the acceleration. So if you have an object with a mass of 2 kilograms and it has the force of 20 newtons, we will take the force, which is 20 newtons, and divide it by the mass. So 20 divided by 2 is 10. The acceleration will be 10 meters squared. Every time you're dealing with the acceleration, it's going to be squared, meters squared. So velocity is distance over time, so that could be, it's usually in meters per square, or in meters per second, but it could also be feet per second. So if an object is traveling 10 feet per second, in 4 seconds, it traveled 40 feet. You could also use a nice calculator here. So let's say an object is moving 5 feet per second, and there's 60 seconds in a minute, so this is feet per minute. Multiply it by 60. So it's 300 feet per minute if it's traveling 5 feet per second. Multiply that by 60, and that'll be an hour. So it would have traveled 18,000 feet in 1 hour if it's traveling 5 feet per second. Now, there's 5,280 feet in a mile. So you divide this by 5,280, and it gets to 3.40 miles per hour. So that's how you figure out miles per hour. So that's kind of a basic tutorial, I guess, on velocity. It's just basically the speed. Go ahead and do it again. Let's say it's 150 feet per second. 60 times 60 seconds for a minute. 9,000 feet in a minute. Times 60 again for an hour, because there's 60 minutes in an hour. 54,000 feet in an hour. And then divided by 5,280, which is how many feet is in a mile. And that's 102 miles an hour. Now, acceleration is different from velocity. Acceleration is the change of velocity over time. So for an acceleration equation, If acceleration is 20 meters per second, so in other words, if the object that is moving increases its speed by 20 meters per second, and the time it took to get to a particular location was 8 seconds, the distance, or the acceleration divided by the time. So we'll do it here, 20 divided by 8. So the acceleration is 2.5 meters a second. So every second that passes, the velocity increases by 2.5. And that is the acceleration if it takes 8 seconds to get to 20 meters per second. Alright, so here's Newton's third law, which says every force or any force will have a action and a reaction. So let's say that the object on the left, the square or rectangle, collides into the one on the right at 20 newtons of force. There's an action and a reaction. The action is the green arrow of force of 20 newtons hitting this one, this object to the right. And once it hits the object at 20 newtons of force, it has a reaction where 20 newtons of force is then sent back towards the opposite direction, towards the, it essentially recoils back. The force that an object collides into something is met with a reaction of equal force. Also, whenever there's a force that collides into another object and there's the reaction, the action and the reaction will be of equal newtons or force, as I said before, and they'll also be facing opposite directions. So if a force is coming this way colliding into an object, the reaction force will go the opposite way. That's why if you hit a hammer on concrete, you'll feel that shock come up right back at you. And that's the reaction force of the impact. So let's say that this orange square is a wall and this yellow circle is a ball. And it's been shot at this wall with a certain amount of force. And it creates an action, which is the force hitting the wall. And it creates the opposite and same reaction, same amount of force back at the ball. So I made a little error describing this, so I'm re-recording the audio. There's also an action and reaction on the ground as well. Since there's an action, two actions and two reactions, it causes the ball to bounce back and the wall to stay stationary because it's on the ground. And the ball is not on the ground. Now let's say that this ball is a person. Yes, I know it's a ball, but I didn't feel like painting an entire person. So let's say that this person is pushing up against the wall, right? So you have someone pushing the wall, getting an action and an opposite reaction, but their feet are on the ground too, and the feet is pushing, which is an additional force against the wall this way. And that's also getting equal opposite reaction from the wall as well. So what ends up happening is neither of the objects move. It's like trying to push over, a wall. From my understanding, if there's more action force than reaction force, there will be an action that takes place rather than a reaction. Now let's say you're in space and the square represents a person and the circle represents a ball, and you're in space and the person is pushing the ball. So what would happen is, because you're in space and you're in a vacuum, there's no friction or anything, once you apply a force, an action force to the ball, pushing the ball is going to push back at you at at the same amount of force that you're pushing it, both you and the ball will be pushed away from each other. However, the ball will be pushed away much faster than you. And the reason why that is because you have a greater mass. So I did 3 tests. I got 90% on this. There's 15 questions. It wasn't too bad. It's just about the laws of Newton laws that we went over. This test was the same type of test, except there are 30 questions. 80%, not too bad. But they had some questions on there that I haven't quite learned yet, so I gotta learn more. And this test was another test, and it was 20 questions and 86%. So that's not bad, I'm pretty proud of it. But so I am studying gravity right now, trying to figure out the constant, and I thought I'd bring something up. This is the constant of gravity, and I'll explain what this is later, but right now I just want you to take a look at this number and what it means. So we got 6.67 times 10 by the power of 11, or squared by 11. Remember when it was, so it's 10 times 10 times 10, how it multiplies by itself 11 times? Well, if it's a negative, it's going backwards. It would essentially be 10 divided by 10 divided by 10 divided by 10 11 times. It's 10 divided by itself 11 times is what I'm saying. So if we go into our calculator, if you got 10, then you want to press this button right here, minus to the 11th power, you would get this number. And that 11 is 11 zeros and a 1. Now, so I wrote that down on this piece of paper. You can't see it right now, but I got it written down. Then I multiply it, because the equation, it was 6.67 times 10 to the negative 11 power. So we got the 10 to the negative 11 power down on this calculator. So now we multiply, like in the equation says, 6.67. Gravity will be our next subject. And that little equation I did before will be relevant soon. So here's a picture of a planet. And I think most people watching this video have a pretty good understanding of how gravity works. It pulls mass or objects towards the Earth, towards the center of the Earth, like here. This is called the center mass. And this force that draws objects towards the planet will pull directly towards the center mass. So no matter where you are on the planet, it'll be pushing you towards the ground. The equation that you just saw me do not that long ago, I spent about 2 hours learning, was me trying to figure out the gravitational pull between two objects relative to the distance, and converting that into newtons. This one took me a little while to get, but I finally got it, and I'm super happy about it. And I'm excited to kind of go over it. After a lot of math and learning, this right here is the gravitational constant. This is going to be really important. It's 6.67 times 10 to the negative 11th power, which turns out to be 11 zeros and 667,408. And that is how many newtons of gravity that's in 1 kilogram of mass. So we're trying to determine how many newtons of gravity or force that gravity is applying to an object based on how far away the object is and how large the object is. So the force, in this case gravity, is equal to G, which is the gravitational constant, 6.67 times 10 to the negative 11th power, times the mass of one object times the mass of another object. So two objects. That could be the moon and the earth, the pole between those two, for example, and then the radius between, which is the distance between these two objects, squared. If you have two objects, and it has to be measured in kilograms, because that's what newtons are measured in. If it wasn't kilograms, you'd have to do more conversions with the calculator. So if you have a 75 kilogram object and a 90 kilogram object that are 5 meters apart, which is the 5 meters is the radius, the r. So this is mass 1 and this is mass 2. What would be the amount of newtons of gravity that attract these objects? So we have the formula here. You have gravity constant, 6.67 times 10 to the negative 11th power, times the mass of object 1, which is, I'll just put M1 and M2. These two are multiplied by each other, then divided by the distance squared. Our new problem, it would be 3 kilograms, two 3 kilogram objects at a distance of 2 meters. What would be the gravitational pull between the two? And I've done this problem many times with the calculator, but it doesn't turn out right because I was watching a video on YouTube to kind of elaborate on it more, and it just, I wasn't getting the right answers. And so it turns out that I think it's because I'm not putting it in the calculator right. So we're going to try putting it in. So it's 6.67. Wait a minute. Still learning here. 6.67 times 10 to the, where is the negative 11. Okay, that's not. Then 75. Oops. We're doing the weight now. Distance between the weight. This is not looking correct at all. Divided by 5. Just gonna go basic real quick, see if this works. 6.67, I'm gonna do the constant times 10 to the negative 11 divided by 3. Times 3 times 3, because 2 3 kilogram objects, and divided by 4, because they're 2 meters away, but it's squared, so it's divided by 4. It turned out to be 1.5 times 10 to the negative 10. So in other words, that's 10 zeros and 1.50. So it's very, very small amount of newtons of force between those two objects. not these ones, but the 3 milligram ones, or kilograms, I'm sorry. Let's say that we have two objects, one 50 kilograms and the other 70 kilograms, and they're 4 meters away. So you'd have the gravitational constant, 6.67, and minus the 11th power, times 60, or I'm sorry, times 50, times 70. That's one big equation. And then 4 meters squared. So we'll do the math of that. Turning out to be 1.45 times 10 over the negative 8th power, which is 0.0000001.45 newtons of force between those two objects of 50 kilograms and 70 kilograms that are 4 meters away, which is very, very small amount of force, as you can see, which is why you don't really feel gravitational pulls towards objects unless they're about as large as the moon or the earth. We're going to figure out an object that's 20 kilograms on the surface of the earth. How much newtons of force is there between this object, object 1, the 20 kilogram, could be a stone block, and the earth, force of the earth. The distance or the radius of the earth is 6.38 times 10 by the 6th power, and the mass is 5.97 times 10 by the 24th power. And so we got those, and we'll plug that in. Here's the equation. We got the gravity's constant, multiplied by the object 1, which is 20 kilograms, multiplied by the mass of the earth, divided by the radius of the earth, from the center of the earth to the surface of the earth, which is where the object is sitting on, squared. Forgot to put a 2 there. So I finally did the calculations correctly this time. I did notice I put 25 pounds instead of the 20. That was just my bad. So we know what 25 pounds is if it's sitting on the earth, how much newtons is applied to it, and it's 244. You could do it is multiply the weight in kilograms, 25, and multiply it by the rate of acceleration of the gravitational pull on Earth, which is 9.807, and it'll come up as 244, which is extremely close to the answer I got using the other method, so it's accurate. Now let's say that you are on the Earth, right? And we want to know what the acceleration rate, or the amount of force that of acceleration that is on the surface of the Earth. In other words, how fast or an object accelerates when it's near the surface of the Earth. So we're going to do the equation. It is gm over radius squared. So g is the gravity constant, 6.67 times 10 to the negative 11. M is the mass, in this case the Earth, which is 5.97 times 10 by the 24th power, and the radius of the Earth, which is from the center of the Earth, center mass, to the surface, or to the object, in which case is on the surface. And it's 6.38 times 10 to the 6th power, and of course it has to be squared. So we'll do that formula. So I typed in the equation, the gravity constant, 6.67, 10, or times 10 by the negative 11th power, and then right beside it is times mass of the Earth, and divided by the radius of the Earth, squared, and it comes up to 9.78. On the surface of the Earth, the rate of falling is 9.78 feet per second squared. So for every second that an object falls on the surface of the Earth or near it, it increases, by each second, it increases 9.78 meters. So for the first second of free fall, it's 9.78 meters. If an object fell another second, it'd be 9.78 plus 9.78 for that additional second, because it stacks. So this is the seconds on the left side here. So 1 second, this is the rate that it's falling at. So this is the acceleration, the rate of acceleration. At 2 seconds, it's falling at this velocity. This is meters a second. At 3 seconds, it's 29 meters a second. At 4 seconds, it's 39. At 5, you get it. If an object fell for 5 seconds, it would not be 48 meters. That was the distance that you fell. It'd be adding all these until you reach the 5th second, because it accumulated over time. The first second you fell 9.78. The second you fell an additional 19.56. So it'd be 9 plus this. Add all these up. When I do the math, the total of all these sums up to 146 meters if you fall for 5 seconds. That's the distance you fall. And I convert it into feet, and that's 481 feet. Let's try to figure out what the acceleration of falling would be if you weren't on or near or on the surface of the Earth, but you're outside of the Earth, like in its atmosphere. And I'll figure out how you do that with the rate, because the gravity is less strong the farther away from the Earth that you go, and you'll find out the rate of acceleration towards the Earth at farther distance from the surface. It's the same equation as you can see. However, we have to figure out the radius between the center of the Earth to the point of the second object out in space in Earth's orbit. And what you do is that's the sum of the radius of the Earth and the radius between the surface of the Earth to the object, which in this case is 3 million meters. We got the equation. We got the gravity's constant times the mass of the Earth. Now we're going to do the radius. The radius, you have 3 million, which it could be written down as 3 to the 10 squared by 6. That's the same, 6 zeros. Adding the two radiuses of 3 million, which is represented by 3 times 10 over the 6th power, and the radius of the Earth, you end up getting 9.38 times 10 to the 6th power. So that's what R is going to be for this equation here. So I'll write that down. 9.38 times 10 to the 6th power. And of course, it's got to be squared. Excuse me, I had to clear my voice. So after doing the equation at 3 million meters from the surface of the Earth, an object will fall at 4.5 meters a second, as opposed to on the surface of the Earth, it was 9.78, which is a pretty significant difference. So that's the formula of determining the acceleration based on the distance of an object relative to the Earth, and the rate of acceleration of it falling towards the Earth based on its gravity.